In this video, we will show how to import data, tidy data, model data, and write a summary of our work. So first we will import the data. We will import the libraries that we will use. We will import pandas as PD. From datetime, import datetime, import numpy as np. Then we will read the CSV file and we will print the first few lines of the CSV file. So it's a traffic quarter hour data. So the CSV file looks like this. There is class column, site reference, start date time, end date time, direction, and count. The printing the shape of the data frame. There is more than 13 million. There is more than 13 million data rows with 6 columns. We check the column data types. So the class, site reference, start date time, end date time are of object time or object type. Start date time and end date time should be of date time type. And the direction looks like is categorical variable. And class looks like it has H and L values, so it's categorical. And count is float 64. So count is all right because that's in decimal numbers. Then we will tidy the data. In this task, we explore the start date time variable to show that not all of the rows in the CSV file are from August 8, 2020. The following code just uses a regular expression search to find offending rows. Use the correct format specifier. So we will do pandas dot to underscore date time. In bracket we will have the column, comma, and we will give the format that we want. So in this, if we look at the data frame, the day is given, and then there is a dash, then month, dash, year, then there is a space, then hour is given, that's 24 hour, and then the colon, and then the minutes. So we will have that format here. So percentage D for days, dash, percentage B for month, dash, percentage capital Y for year, and then space, percentage capital H for hour, colon, percentage capital M for minutes. And we will save this as a new colon, start underscore date underscore time, printing the first few lines. So we can see the start underscore date underscore time is printed over here, and that's in date time type. Then we will grab the data rows whose start date time is not 8 August 2020. So we will do df and square bracket, and then we put the things that we don't want. So the column start underscore date underscore time, we want the days which are not equal to 8, and we put that in bracket and put end in between and put another bracket, and we want the month not equal to 8. So we'll assign that to not 8 and printing not 8. We see that all these start date time doesn't have the day has 8 and the month has 8. So there are about more than 8 million rows. There are over 8 million offending rows. The following code drops them from the data set. So we will drop the rows that does not start on 8 August. So we have DS square bracket, and then inside this pair of bracket we will have day equal to 8, so this double equal sign, and pair of the bracket, and month equal to 8, and we will check the size that's more than 900,000 data rows. We will explore the data. So we will create a plot of the distribution of the count variable. We will import Seaborn as SNS. We will import matplotlib.pyplot as PLT. And we will run this import awnings, and we will filter the awning signs. We will get awnings with a density plot. So we will filter the awnings. Then we will create the density plot with Seaborn. sns.kde plot of count, and this is how it is printed. So we can see that the data is mostly close to 0. This shows that the variable count is heavily skewed. Now we collect data rows with count values less than 10. So in August 8, less than 10, we have the count data less than 10. So checking the head of it, so we can see the count column, the data is less than 10. So we'll print the density, we will create the density plot with Seaborn. sns.kde plot of count. So this is how it looks like. So still mostly the data is concentrated around 0. This shows that the variable is also discretized with peaks at whole number values, and there are a lot of 0 values. So we will create a figure with desired size. This is how we do that. So PLT, which is matplotlib.pyplot library, dot subplots, and bracket figure size equal 10. This is the size of the width, and 6 is the size of the height, and it's in inches. Create a box plot of count values against data. So sns.boxplot, open bracket, X, which is the horizontal axis, that will represent the hour, and Y, which represents the dependent variable, that's the value on the vertical axis, and that is count. And we will also show the means, and that is printed inside this figure that we created of size width equal 10 and height equal 6. So we will put Ix equal Ix, close the bracket. plt.x label, this will change the label of the horizontal axis, which we want hour, and we change the label of the vertical axis, which we want count, and we'll put the title box plot of hour versus count, and plt.show, open and close bracket. So this is how it is printed. Then we will transform the data. Further subset the data to eliminate rows where the start time is before 8 or after 18:00. So we want the data to be from 8 a.m. to 6 p.m. 18:00 is 24-hour clock. So this is how we do that. August 8, square bracket, and then inside the pair of brackets we will put hour greater than or equal to 8 and August date. So we want hour to be less than or equal to 18 and we'll close the bracket. So printing the first few lines, we see the start date time, the hour part is more than 8 and less than or equal to 18. Check the dimension of data rows. So when we check the dimension of the data row, this data frame that we created, there's 64,240 data rows and 7 columns. Create a new variable scount, that is the square root of the count variable. So we will use numpy to find the square root. So numpy was imported as an np np.sqrt and open bracket the name of the data frame and then square bracket the name of the column count. So we'll take the square root and save it as in the new column scount. So checking the first few lines of this new data frame, we get a bit of warning sign over here. It says use dot location equal value instead. Okay, but it's done. So let's work through it. So scount column is created and is the square root of the count column. Then we will plot the distribution of the new scount variable. We'll create a figure with the desired size. So we want the subplot to have a figure size with 10 inches and height 6 inches. We'll create the density plot with Seaborn, sns.kde plot of scount, and we want it printed inside this figure that we created, ax equal ax. So this is how it is done, and still we see most of the values close to 0. There is still a clear skew, but things are a bit better than before. So model, we will now fit simple linear regression to predict the scount values. We will work with a square root transform applied to a working day subset of the data. Replace the values in class variable with digits. So in the class variable, we see that the values are H and L. So we want to replace that with H with 1 and L with 0, and we will save that as a new colon class replace. So printing the head of it, there is a little bit of error. It says use dot location instead. Okay, we will leave this. We won't do this in this one, in this lab. So class replace now contains 1 for capital H and 0 for capital L. Then we'll check the data types. So August date dot D types contain this. So we see that start date time, we have date time 64, scount is float 64, class replace is object type. We'll change the data type of class replace as type int. Now the purpose is if we change it to int type, we will be able to use it for simple linear regression. This is a time series data, but we want to create simple linear regression. Convert the data type of class replace column to int. So this is how we do that. So column here dot has type pair of brackets, and we will have int. Checking the data types. So again we see that class replace is of data int 32. Now we get a bit of error again, the dot location, it says use dot location instead. Then we will generate training and test set, where the training set is 90% of the data and the test set is only 10% of the data. So from sklearn dot model underscore selection, we will import train underscore test underscore split. So split the data into training 90% and test 10% sets. So x underscore train, comma x underscore test, comma y underscore train, comma y underscore test equal train underscore test underscore split of this class replace column, comma, and the y column, the dependent variable, we want it to be scount. So we'll put over here, comma, test size equal 0.1. So that's the decimal value of 10%, comma, we'll add random underscore state equal 42, because otherwise all the values we will get in each run different values. Fit linear regression model. So from sklearn dot linear underscore model, we will import linear regression. So, and then model equal linear regression, open and close bracket, and then we will fit the model. Model dot fit pair of bracket pandas dot series of the train data dot to underscore frame, open and close bracket, comma, the dependent variable y underscore train. So this is where we fit the data, and we calculate the root mean square error. So the root mean square error is the observed value, the values that are given, minus the predicted value, and we will take the square, then we take the average of it, and then we take the square root of it. So this is how we do that. We use numpy here. So np dot square root of np dot mean of np dot square of y, the test values, minus the predict. So we will do the prediction over here. Model dot predict bracket pandas dot series of x test. So the independent test values dot to underscore frame, and then close the brackets. So we have 5.07 and so on. So that's the model root mean square. Then we will calculate root mean square error for the mean of the train values. So we have the test values, and we will separate the mean of the train values. So we take the square, we take the mean of it, and then we take the square root, we get 6.564 and so on. The linear regression model performs better because the root mean square error is less. Roughly speaking, the predictions of our best model are on average within 25 of the actual count. So 5 squared is 25. Given that most counts are less than 10, this is not great performance, and we would ideally be able to find a model that had better predictive performances. So this is a time series model, as we know, so we'll be able to find a model that performs better. then we replace our data. So we will create a data frame of the test independent variables and the test dependent variable and the prediction from the model. So we will create the data frame here. So pd dot data frame pair of bracket, and then we will put the pair of curly braces because we're creating the dictionary here. So x colon, so that will x will represent the test values of the independent variables, and y will represent the test values of the dependent variable, and y underscore predict will represent the model prediction values of the test values. So here what it looks like. So there are 6,424 values, data rows. We'll create the plot. So the subplot, so plt.subplots, and then we create a secondary axis for the second data set. So we will have x2 equal ax.twinx. This is where we share the x-axis with this figure, which is ax, and then we will set the same limits for both vertical axis. So AB equals 0 to 47, x set and x under dot set underscore y ylin, that's the y limit, is from A to B, which is from 0 to 47. x2, which is the second vertical axis that we created, we'll set the limit for that dot set underscore y lim, y limit from 0 to 47. We'll plot the original data points and the regression line. SNS dot strip plot bracket x equal x, comma y equal y, comma data equal data, comma color equal white, edge color equal black, line width equal 1, and that is printed inside this figure. X equal x, add a horizontal line at y equal mean. So here we will create the horizontal line, so for the mean value of the trained data. So x dot xh line bracket y equal np dot mean bracket y underscore train, comma, that will be, the color will be green, comma, line style will be dash, line width is 2. Then we will create the point plot, SNS dot point plot bracket x equal x, comma y equal y underscore predict, comma data equal data, comma color equal red, comma markers equal all, comma line style equal none. So predicted values are represented by red dots, and that will be printed on x2 vertical axis. Then we will set x and y labels. So x dot set open and close bracket x label equal class, x dot set open and close bracket y label equal s count, x dot set open and close bracket x tick labels equal square bracket L comma H. So L will put for 0, H will put for 1. So this is how it looks like. So we can see the predicted value over here. And these are the test values, the black dots. And this is the predicted value. And this green line is the average of the train data, the train Y values. So we see the predicted value for L light vehicles is more than the train average data, and for heavy vehicles the predicted Y value is less than the average. The summary: in this lab we explored the traffic count dataset. The count variable is highly skewed, which is unsurprisingly given that it is bounded below by 0. There is also clear periodicity in the data, again unsurprising because this is a time series dataset. Regardless, we reduced the dataset to daylight hours and used a square root transform on the counts to get a less skewed variable S count. We then fit two simple models using a training set and compared their performance on a test set. A simple model that predicts the traffic count based on vehicle class performed better than a model based on the overall mean count, though this still leaves a lot of variation in the data unexplained.